Alright, this is going to be the friction homework. Castle Learning walkthrough 3G friction. So let's take a look at number one. Number one. Which arrow represents the direction of the frictional force acting on the box? Well, the definition of friction is the opposite force, opposite the direction of motion. Alright, so if the box is sliding down, if the box is sliding down, and that's B, well, the friction is going to be opposite the direction of motion. And so if the arrow of B is the motion, well, then the friction is going to be the opposite way. And so it's going to point northeast, and it's going to be D, right? D is your answer. D is your answer. Number two, a 0.5 kilogram puck sliding on a horizontal shuffleboard court is slowed to rest by a frictional force of 1.2 newtons. What is the coefficient of kinetic friction between the puck and the surface of the shuffleboard court? So the mass is 0.50 kg. Alright, and it's slow to rest. So the final velocity of the puck is 0. And the frictional force, they tell you that the frictional force is 1.2 newtons. What is the coefficient of kinetic friction? So they want you to know what mu is. Mu, it doesn't matter. The coefficient of kinetic friction between the puck and the surface of the shuffleboard court. Now, since we're talking about friction, alright, we know that our frictional force is equal to mu times Fn. Well, we know what mu is, right? Well, we don't know what it is actually. We want to find out what it is. We know what frictional force is. We know what that is. But we don't know what Fn is. We need to know, right? We need to know what our normal force is. Well, if you think about it this way, start drawing a free body diagram. Free body diagram. Let's go with this body diagram. And if the object is not moving up or down, you know that your Fnet in the y direction is 0. Alright, if you know that your object is not going up or down, you know your Fnet in the y direction is 0. This is something you guys should know. Alright, now why am I separating into y and x direction? Because x and y, for now, I want you to trust me. Right? X and y don't mix. Alright, for now. Just accept this fact to be true. Things that act in the x direction and things that act in the y direction don't mix for now. We cannot mix them. So right now, I'm just solely saying that Fnet in the y direction is 0. Well, what's the sum? What are forces acting in my y direction? Well, we know Fn is, and we know what Fg is as well. We know that Fg is as well. Now, well, if Fnet is the sum of all forces acting in one direction, well, the only forces acting in my y direction are Fn and Fg. Right? And then we get is equal to 0. So, if you look at all of this again, let's go back to the previous minutes, but I'm going to erase all this. So here's what we established so far. Fn, Fg, So Fn, if F net in the y direction is 0, we know it's 0 because that's not moving up or down. For the most part, you can assume that in all friction problems, this should be the case in the y direction only. It's possible for the x direction to have an F net of 0, but not all the time. And we know that the total forces acting in our y direction are just normal force in g, force due to gravity, only y direction. So if we solve for Fn, we get negative Fg. All I'm doing here is subtracting Fg from this side and adding it to this side. I mean, subtracting it from this side. Well, we also know that Fg is ma, because Fg is your force due to gravity. It is your force due to gravity. Now, well, what is my force due to gravity? Well, my mass is, what's my mass? It's 0.5. 0.5, and a is, well, you know what your acceleration due to gravity is. It's negative 9.8. Negative 9.8, 0.5, and you get negative 4.9. 4.9. And so that's going to be force due to gravity, newtons. Well, then if you plug this in over here, you're going to get negative 4.9 is equal to 4.9 newtons. All right. And so that's your normal force. That's your normal force. Well, we're still not done. Because we want to solve for our coefficient of kinetic friction. Well, let's go back to our formulas again. Our frictional force is mu times Fn. We know what frictional force is. It gives you what the frictional force is in the problem. Mu. Want to solve for it. And we know what Fn is. Our Fn is 4.9 newtons. 4.9. Now divide 4.9 from both sides, and you get 1.2 divided by 4.9 is somewhere around 0.6, right? Somewhere around there, somewhere around there. And so the answer is C. Number 3. Well, that rhymes. Perfect. An 80 kilogram skier, so your mass is 80 kilograms, slides on waxed skis. Slides on waxed skis. So you probably need your reference table for this because it's mentioning waxed skis on snow. So sliding on waxed skis on surface snow at constant velocity while pushing with his poles. What is the horizontal force pushing him forward? Well, think of it this way. If you're traveling at a constant velocity, you must be in equilibrium. Must be in equilibrium. And if you're in equilibrium, then your F net is 0. F net is 0. Alright. Well, F net in the x direction is 0 at least. But overall, your F net is 0 if you're traveling at a constant velocity. Now, what is the horizontal force pushing him forward? Well, if we draw a free body diagram, that's normal force, and that's force due to gravity, and that's force applied. Okay, and this is, we make this a bit longer. Make this, alright. This is your force due to friction. Well, if your F net in the x direction is 0, well, what are the only forces acting in the x direction? Well, it's just your applied force and your frictional force. And so you know that's going to be 0. Well, FA is equal to negative FF. Okay? All I did here was subtract frictional force from both sides. And I know that my horizontal force pushing me forward is equal to my negative frictional force, which means we want to find out what frictional force is. Right? Well, there's an easy way to figure out what that is. I went over this with your notes, I think. So your frictional force is equal to mu Fn. Well, we established in number 2 that if your y direction, well, if your Fnet is 0 in the y direction, then that must mean my Fn is equal to negative Fg, because the sum of all my forces in my y direction are 0. Which then, well, let's solve for Fn first. So Fn is equal to negative Fg is equal to negative Ma, which is negative 9.8. We know my mass is 80. Alright. And so then I get somewhere around negative 800. Let's see if this works. So, well, it's going to be a positive 800 because negative times negative is positive. So you're going to have a normal force of 800 newtons. Well, if you look at your reference table, you're going to see that waxed skis on snow, your coefficient of static friction, or coefficient of kinetic friction, because again, you're moving. So if you're moving, it's kinetic. Moving, kinetic friction. Your coefficient due to kinetic friction is, for wax skis on snow, on your first page of your reference table, is 0.05. So now you have U. Now you have Fn. All you're going to do is plug it into this equation, and then you get the answer. Alright, so you get, I'm going to assume divide by 20, somewhere around 4. Somewhere around 4, I think. No, 40. It's 0.05. Yeah. It's 40. So it's going to be 40. C. Let me just make sure real quick. 40. Give me a second. Alright. Number 4. A car's performance is tested on various horizontal road surfaces. The brakes are applied, causing the rubber tires of the car to slide along the road without rolling. The tires encounter the greatest force of friction to stop the car on what? So this is where you must use your reference table again. Alright, so how do I use it? Well, if you look on the first page, bottom right, approximate coefficients of friction, you'll see all these coefficients of friction. I don't know what else to say other than repeating it. So the higher your number, the greater the friction will be. The closer to 1 you are, the more friction you will encounter. So all you're doing here is looking for which gives you the highest number. And since the car is moving, you know it's kinetic friction. We should look at kinetic friction. So you go through every one of these, you'll see that rubber on concrete dry gives you the highest friction. So it is A, dry concrete. 5. Compared to the force needed to start sliding a crate across a rough level floor, the force needed to keep it sliding once it is moving is less. We talked about this. If I apply a, well, if the object's not moving, we know it's static friction, okay? Object not moving. The only friction it will experience is static, well, let's just call here static friction. Well, if I apply a force of 10 newtons on a box, for example, let's say this is a box and I apply a force of 10 newtons, I'm trying to push it to the right. Well, if it's not moving, then my force due to static friction is also 10 newtons back. It's opposite. And so if these two forces are opposite, then we know my F net is 0 and my object is not moving. So this is static friction. This is a static frictional force. And, and then once, well, let's say to get this box moving, I have to apply a force of 10.1 newtons. To get it moving, I have to apply a force of 10.1 newtons. Well, once I apply a force of 10.1 newtons, kinetic friction is going to start taking place, start going to take over. And so my kinetic friction is going to be less because we talked about this in class in real life scenarios. It's harder to get something to move than to keep it moving. It's harder to get something to move than keep it moving. That harder to get moving is static friction and it requires more force to overcome. Whereas once you're ready getting it to move, your kinetic friction that you experience is less. It is always less than the maximum static friction needed to move the object. So the force needed to keep it sliding once it is moving is less. Now, I kind of want to just explain the idea of friction again if you weren't paying attention in class. Imagine, well, if you take a look at all your surfaces, you might think it's flat. You might think it's flat. You might, let's say, a box and then box and it's a flat box over a surface and it's a chair. And let's say that's a computer. Well, if you look at a microscopic level, you'll see that they're not actually flat. They have these jagged surfaces, these grooves, and the surface, the desk also has the same exact thing. It's not going to be exactly straight. It's going to have these grooves, these edges. And what causes friction is when these surfaces move against each other, they rub against these jagged surfaces and it causes resistance to motion. It causes friction. And when objects are just sitting there, these grooves, they go down. They how do I say it? They combine more. They settle in more. Because if you think about it, that settling in is just molecular bonds, bonds being formed between these atoms. And if you don't want to think about it too far, just ignore the atoms part. Just know that if it's harder to get something moving than to keep it moving, so you're going to need more force to get it moving. Number 6, according to a reference table, approximate coefficients of friction was the minimum horizontal force needed to start a 300 Newton steel block on a steel table in motion. So they want the minimum horizontal force. So they want to overcome the static force, right? To get an object moving, you must overcome the maximum static frictional force. Well, it's a steel on a steel block on steel. Alright, so if you look at your reference table and you know that you're looking for static friction, you know that your mu is 0.74. Well, you know your frictional force is mu times Fn. And so your mu is going to be 0.74, and your normal force is going to be equal to your weight, right? Your normal force is equal to negative Fg, We know that the 300 Newton steel block, well, that's its weight. We know that another term for force through gravity is weight, and so your weight is 300 newtons. So if your weight is 300 newtons, it's that, and then Fn. The reason why ignoring this negative sign over here is most likely because they excluded the direction. Just know that your normal force can never be negative. Well, it can be negative depending on direction, but if you know that, well, if it's sitting there, if the box is sitting there, and you know this is your normal force, it's going to be positive, okay? It's going to be positive, and down is negative. Down is negative. The question is just omitted that number. Now, 0.74 times 300 is going to be D, 222. 222 newtons. And so that's the answer. That's your frictional force. That's the minimum frictional force you must overcome to get the object to start moving. Number 7. What is the minimum horizontal force needed to start a 300 kilogram steel block? So the mass is 300 kg. That's not the weight this time, it's kg. Steel block on steel table. And so, what's the minimum amount of force? That's 0.74. Now, they're not asking you for, they're not giving you the weight. They say 300 kilogram steel block, not a 300 Newton steel block, a 300 kilogram one. But you still have to figure out, well, what is my frictional force? And they're asking you, what is the minimum horizontal force required to get the box to move? It is static friction, so you're solving for static. Solving for static. Well, you're solving for static friction. And when you talked about this, you know Fn is negative Fg. So what is your mass? So we know Fg is ma. What's m? 300. And what's a? Due to gravity, force due to gravity, negative 9.8. And you get a positive 2,000, somewhere around 3,000, somewhere around there, right? Somewhere around there. And so now that you have your Fn, you can substitute in here. You're substituting your u, your mu, and you get somewhere around this number. So you need a frictional, this is your minimum horizontal force required to get an object to start moving. Hopefully that helped. Ask me any questions if you do have any questions.